let's see the right. I go on kodumu the one of the application we discussed, and second one, right, the motion of a particle or an object under gravity, right? The second application, right, that's motion of an object under gravity. This also applies the you can apply the mechanical energy conservation. Let's see how. I will consider that we projected an object from ground vertically upward with an initial velocity u. So we already know that when it is moving and they come to the maximum height, then the velocity becomes 0 at height, and between this velocity decreases in the time, right? So because it's in under gravity, it's moving with the deceleration, acceleration, not the acceleration here, but the gravitational deceleration, the minus g we use it, right? And then the total height of the object is reached the maximum height is reached, like on capital H, and this is the point A, and this is position B, and this position I am considering as C. At this position, the height from the ground, let's say h, and the velocity in that position we consider as v, right? So let's write there. Let's write. Consider an object of mass simple m. An object of mass simple m is projected vertically upward. Is projected vertically upward with an initial velocity u. With an initial velocity u, and then you can draw this diagram. So okay, you draw this diagram. Then this velocity v and this height, the relationship between this u v, we can get using equations of motion. I'm considering this level. This is a reference level, right? That's a potential energy 0 level. This we consider the actual level, you know, potential energy is not 0 at this level. We will consider that with respect to this level, all the measurements will be taken, right? So then I'm using v square equals u square plus 2as first. So from A to B, and then I can find the velocity at v. So v square, let's say, equals u square plus 2 is minus g and simple h there. From here to here it is simple h is the height is moving, right? So then I write v square equals u square minus 2gh, and the same thing I can do for A to C. And upward, the v square final velocity is 0, u square minus 2g capital H. So then capital H and u, they are having a relation, just u square over 2g. So already we know that. So I will write this to write the energies and velocities. That I will write the kinetic and potential energy or these different places there. Okay. So I am writing the equations for the energies. Let's see. At this position, first we consider the potential energy. The potential energy at this position is 0 taken, right? Here this level I am considering as the potential energy is this topic. So write as there. the potential energies, and at this level potential energy is 0, and here the potential energy at this level, that's mg simple h, and here the potential energy that's equals to the mg capital H, right? At these different places. Now the kinetic energy we consider, kinetic energy at this position, this kinetic energy, that's the velocity is u, that's half mu square. Using this equation, you can write this u square equals 2g capital H. So you can substitute there. This half m, instead of u, that is 2g capital H. So then 2 cancel, and then it's become mg capital H, right? That's a kinetic energy at point A, and B, the kinetic energy is there. So I'll mark it this, that is equals to the half m v square. This v you can substitute from this equation, right? This is half m v square, instead of that is you can have u square minus 2gh. So now you can write as half m u square is mgh, right? Minus this mg simple h. This is the kinetic energy at this position, and the top most position, the kinetic energy is 0 because no velocity. So velocity is 0. So then kinetic energy is 0 because of the v0. So that's the kinetic energy 0. It's a kinetic energy thing. And finally, I will take the total energy. Total energy corresponding to this, that is the sum of these two. This kinetic energy plus potential energy. The kinetic energy is 0, potential energy is mg capital H, and this level the total energy sum of these two, that is this mgh potential energy minus plus potential energy is mg simple h, and this is mg capital H minus simple h. So then these two cancel, and this total energy is mg capital H. And here also total energy, potential energy is 0, the kinetic energy equivalent to mg capital. So you can see now, during this motion at any point the total energy remains same, total mechanical energy remains same, that's mgh. But when it is moving up, the potential energy increases and kinetic energy decreases. So that's happened. What's happened then? This reduced potential energy converted to the kinetic, then the total energy remain same, right? So that means you can apply this energy conservation, that's a mechanical energy conservation for the motion under gravity, because when the object is moving under gravity, the only force acting on it, the weight, that is a conservative force. If that's a conservative force, that the work is doing under the conservative force only, you can apply this mechanical energy conservation. It's clear? So okay, note it down there. Okay, note it down. These are the velocities I am finding. You can write it separately and then write. I will use this same levels to write them. You can get idea. The energy is in during this level, and energy is this level, and energy is other level. right? I think right. Then they write something there. Right. Therefore, the total energy of a body, total energy of the object remains, total energy of the object remains constant at any position during its motion under gravity. At any position during its motion under gravity. If I consider this as a graphical way, you can see like this, right? You know that at the common height, right? So at particular height, that's potential energy is mgh, right? So you can write this as this is potential energy, that's mg, that is y equals mx type graph. If we consider about this kinetic energy, that's Ke minus mg times h plus the mgh. Mgh, capital H, is a constant value. So then you can write this as an equation y equals minus mx plus c type graph. At the kinetic energy decreases with the height. The potential energy increases with the height. The total energy we consider, so always mg capital H. So it's a constant. So this is just a y equals constant type graph. Right? So when you represent this in graphically, it's the height, this is energy. You can get the potential energy graph is the potential energy graph. And the kinetic energy graph will be like this. Y equals minus mx plus c. That is a kinetic energy graph. And then the total energy is a constant, so that will be this time. This is the total energy graph. Mg capital H is the total energy. This each case you can say this part, this point and this point. Sum of these two, that's equals to this one. And here same potential and kinetic energy is same. So then this part and this part is same height. You can write. You can draw the graph like this. That's the energy change with the height. We can draw the energy change with the time also. Try to draw it. First you note this down and how it is comes in, and then draw the graph how this kinetic energy, potential energy and total energy changes with the time. So try to draw it. how you can draw it with the time, how you can get the potential energy that's equals to the mgh. You can write this in time as a particular height. You can use s equals ut plus half a t square, the height h, ut half t square. Then this is minus to t square plus ut. Substitute there. Mg then now will multiply by this. There's minus m t square over 2 t square plus mg ut, like that. This is just similar to the x square plus that is a quadratic equation, right? There's quadratic relation there. So it's minus x square like this equation. So then the energy increases is the time. The time potential energy you can draw is increasing like this. And when you consider about the kinetic energy, similar way you can write kinetic energy, that's equals to the half m u square, that's v square. V you can write is u plus at, half m u plus at, that is square of that. So then this is by simplifying, you can write as half m, that is u plus at. You can write this is u minus a dt, right? Because the v equals u minus dt when you are moving up. Good. So then you can write this is mu square minus two u gt plus t square t square. It is then half m g square t square plus minus m u g t plus half m v square. So the quadratic equation, right? So then the energy you can write as here at t equals 0, these terms are 0, but initially they are having this much of it. So it's starting from topmost point and then it's reduces, so it's with the graph like this. The total energies remain constant. So if you draw this all the graph at same way, this potential energy increases, kinetic energy decreases, and total energy remains same. It's a curve now. This is for potential energy, this is for kinetic energy, and this is for total energy. So this is the way you write drawing the graph, right? With the time, the previous we draw with the height, now I'm drawing it with the time, how that energy changes. I'm focusing this kind of one because some cases the MCQ type questions they focus on these types, or how it changes with the time, how it changes with the displacement. So they ask me which graph is represent this one, which one is some fault one, like. So then you need to know that how those energy changes with the time, how the energy changes with the height, like that. So okay, then I'll erase this. If you have any doubt, you can ask, right? Okay, I think it's clear then. Okay, then I the third application, motion of a pendulum. it is. Right, then the depreciation motion of a pendulum. It's also can base the mechanical energy conservation. So I will consider a pendulum so the pendulum I'm considering. And I'm considering different places. It's the path of the pendulum motion. The pendulum is L. Let's write there. Consider a pendulum of length L and mass m. Length m, so length L and mass m. Consider a pendulum of length L and mass m. First you draw this one. Positions I'm considering as ABC. And this level I'm considering that potential energy is 0. And to this point is the capital. Velocity is also marked. Mass of this bob is m. You can see here when the bob is moving, the tension is there, and also weight of the bob is under. It's downward always, right? Weight. Let's draw this one. Right. Here the velocity v1 and this side the v, and this is initially so no velocity, we can raise it up to this point and then release, right? And in this system, the forces acting on this body during its motion is the weight of the body and tension of the string. The tension of the string is always perpendicular to the direction of its motion, so then the tension will not do any work, right? The motion, the work done by the tension is zero. Here the work is done only by this weight. The weight is a mechanical, that's a conservative force. So then when during this motion there is a work done only by its weight, that is a conservative force. So that means the mechanical energy can be conserved because no non-conservative forces acting in the system to reduce the energy or lost the energy, right? So then we can apply the mechanical energy conservation. So then we can say that the total energy at this point A and it's equals to total energy at B and it's equal to total energy at C. So then you can write the equations correspondingly. You can write the potential energy plus the kinetic energy for each point and then equate it. So that's the way you are trying to draw equations under these sessions, right? We'll discuss some examples. First we write there, in this motion, the forces acting on the bob of the acting on the pendulum bob, the forces acting on the pendulum bob are first one, right, tension of the string, second one, right, weight of the pendulum, they write there. Right, the tension of the string is always perpendicular to the direction of the motion. Therefore, the work done by the tension is zero. Right. Therefore, the work done by tension is zero. Right. Then work done by the system is only by the weight of the body or weight of the object or bob, only by the weight of the body. Since the weight is a conservative force, the total mechanical energy of the system total mechanical energy of the system is constant. So therefore you can apply them. The total mechanical energy at A, that's at the point A, that's equals to the V equals to the total mechanical energy at B, that's equal to the total mechanical energy at C. The total mechanical energy at A is, that's kinetic energy 0, potential energy with respect to this point is mg, capital H, and this P, at B you can write as a potential energy is, kinetic energy is half m v1 square, mechanical potential energy mg simple H, and that's equal to half mv square plus mg. Sorry, it is 0 because its potential is 0 level. So you can write the equation in this way, and then equating you can find what the unknown you know. I'm not going to simplify or write like this. That's the way you are writing, and each point then you can get the values, so answers. You need to ensure that this work done under conservative forces. You can note it down, okay. Alright, next one, right? There is third application, the last one. I'll give the 4 applications only, then we discuss some questions. Right, and motion of an object, which attached to a spring, attached to a light spring. Motion of an object attached to a light spring. We are considering a spring system. This is the object, right? Consider that the spring has friction constant K, right? So when it is stretch and then release, right? Stretch and release. This is the maximum height. So when it is released, moving from here, velocity v, the mass of this particle m, right? And this extension x. Then let's see how to write the extension. Just write there. What are the forces acting on this? So that's a spring force will act on the particle during this motion. So spring force is a conservative force. So then we work under this case only under the that's a conservative manner. So then you can apply the energy conservation. Give me 1 minute, please. Okay, first write under this, first write. Consider a light spring of a spring constant K. Consider a light spring of a spring constant K and mass simple m is attached to it. And mass simple m is attached to it. Okay. Then draw this diagram, and during this motion the force acting on the body to make the work done, right? So it is only the spring force, right? If you can write it as a case, right? That's it. Force acting on the object is spring force. Only spring force. Only spring force to do work. Right? since it is conservative force, since this is a conservative force, total mechanical energy is conserved. Therefore, we can write what is the this energy at this position. This kinetic energy is 0. That's only the spring. That's it. Some energy stored in the spring, that is half kx square, you can write. And when it is released, this come to this position, and here when it's moving with velocity v, that's half mv square. There's no any potential energy. That's elastic potential is not there then, because that x becomes 0 then, right? And in between these two, and in somewhere here, any point, there also, let's say that's extension x1 or something, and you can write that is a kinetic energy, say half mv1 square plus half kx1 square. In between this, any point in between this position, you can write store both the kinetic and elastic potential energies there. So you can write the equation in this way by using the mechanical energy conservation. So energy at one place you can equal to the energy, total energy at another place. Ensure that the work is done only by the conservative forces acting on the system. To copy it down, then we discuss some question. Copy it down first. Right. All right. Okay, right. Then write an example. First example, I'll give you this way, right? Let's think. Conceptual question එකක් වෙනවා, right? then we have in figure 1, right? In figure 1, the man works 2 meters in figure 1, the man works 2 meters man works 2 meters carrying a mass of 15 kilogram, carrying a mass of 15 kilogram. Carrying a mass of 15 kilogram on his hands, on his hands. Then write in figure 2, on figure 2, he works the same distance, he works the same distance pulling a rope he moves the same distance, pulling a rope, pulling the rope behind him, pulling the rope behind him. Pulling a rope behind him. The rope goes over a pulley end. The rope goes over a pulley end. Goes over a pulley end. Mass of 15 kilogram hangs. Mass of 15 kilogram hangs at its other end. At its other end. In which case is the work done greater? In which case is the work done greater? Can you tell me which case is the work done is greater? Just answer क्या बनेगा? First one is work done is greater than second one. You need to consider that both the cases the size of the man is same, right? The same weight, same. When I'm drawing, it's much one is bigger, second one is smaller, but it's not a scale diagram, right? Is it first one? How it's become first one? So if you know, let's consider in the first case that's the work done by the man against the gravity is 0, right? That's because the granny is moving horizontally, gravitational, then only this system they having weights downward, and the normal reaction on hand is upwards. That's only. Move the distance some distance will be there. So let's see, it's in the friction, they have to do work against the friction. So then the work done by gravity here is 0. But here to do this work, so that's range G and then tension T, and he need to apply the force same way. So some force you need to apply, right? The force, that force is let's say equals to the tension apply. Let's say the man pulled the rope in horizontal, the tension, same tension is equals to weight of this block here. So then the work done by the man, then this work done should equals to the, let's say, weight, or that's the tension multiplied by the displacement. That's a 2 meter they will travel. In the first case, there's no force acting on it, right? No force acting on it in the direction of its motion, so no work done. Yeah. Literally lift it up. I lift karang in a potential energy, so in the same potential energy is there during its motion also, right? And so here they need to do work. So second figure they have the greater work. You can write. I will give the answer. You can write. Just write. First main figure ka lang yun. First figure. The work done by the man against gravity, because that gravitational force acting on it is only. The work done by the man against gravity is 0. In this first figure, right, is 0. Because displacement of block is perpendicular, because the displacement of block is perpendicular to the force applied by him on the block. Force applied by him on the block. That's capital R, right? So then write in under the figure 2, the work has to be done against gravity. Work has to be done against gravity. That is equals W equals the tension into the displacement. W equals tension into displacement. If you think that string will hold horizontally, that tension is here equals to the weights. The weight multiplied by the distance, 2 meter distance. You can write in that way also. You can write in addition to this, work is to be done against friction. Work is to be done against friction while moving a distance 2 meter. While moving a distance 2 meter. Thus, the work done in case figure 2. Thus, work done in case figure 2 is greater than in the case figure 1. It's greater than in the case figure 1. Okay, then write another question. A body moves from point capital A, and let us then write a body moves from point capital A. Body moves from point capital A to capital B. A to capital B under the action of a force. Under the action of a force. Under the action of a force varying in magnitude as shown in the figure. Varying in magnitudes as shown in the figure. Right, obtain the work done. Obtain the total work done. Force is expressed in Newton and displacement is expressed in meter. So I will get, sorry, it's not the time, it is the displacement. displacement is expressed in meter. I will give you the graph with the values. This one. Okay, that is the total work done. What is the answer? Right, that answer is correct, right? You need to consider all the areas. Here, this area, this one, and this one would be radius. So how we can get this area? That I'm considering as A1, A2, A3, and A4. Total work done is this area of sum of the area of these and subtract this last one. And this area you can write that 10 into 1. And this is trapezium, that is 10 plus 15 divided by 2 multiplied by 1 is meter, 1 meter, and this is half height is 15 and so on, minus this is also the half 15 and 1, so this will cancel these two. 10 plus 12.5, so it's 22.5. That's the total work done during this, right? Okay. Another question. You write there. Write another question. An object of mass 5 kilogram falls. The object of mass 5 kilogram falls. An object of mass 5 kilogram falls from rest through a vertical distance of 20 meter and reaches with a velocity of 10 meters per second How much work is done by push of air? How much work is done by push of air on the object. Push of air on the object. Okay, quickly do this one also. හරි Okay, how we can do this? Now let's see, let's weight of the body. It is 5 kilogram. Let's drop, right? Drop a fall from rest. Here this work is done. Let's see this done by the gravitational force and the push of air, the upward, right? The forces acting on this body is then the weight of the body and the push of it, that is mean the air resistance. So then the work done by gravity we can write, it's fall the height given 10 meter, you can write as work done by gravity. Work done by gravity, that is let's see, WG, it's equals to the weight multiplied by the height, vertical height. Oh sorry, it's given 20 meter, not 10 meter. So it is mg into 20 mg, right? Then the work done by the push of air, that is WF, let's see. Let's take WF, that's why that's the thing we need to find. They are asking that the work is done by push of air on the object, right? We need to find this. Then how we can relate this as total work done, which equals to the kinetic energy change. So that is the work energy principle, right? Using work energy theorem, you can write as total work done kinetic energy change, changing kinetic energy. Total work done is work done by gravity plus work done by the push of air. And kinetic energy change, the question gives that it's reach a velocity 10 meters per second. So this half m 10 square minus, initially it's dropped from 0, so 0 velocity. Now you can write, this is that is 20 mg WF, then this is half, so that's 50 m. G is 10, so then you can write in, after this you can write that WF equals 10, this 20 mg is 20 is 50, the 5 into 10 is plus, sorry, WF equals to the, that's 50 m minus 20 mg. Now substitute values, 50 into 5 minus 20 into 5 into 10. Sorry, not 20 mg, it is 20 m only. Now 20 mgh now. mgh, right. 150 minus 1000, that's 750 minus 750 joules. Why it's minus? Because it's that work is and against the friction. Against the air force. The resistance is opposite to the direction of motion. So that's why it's minus. So the 750 joules is done. 750 joules of work done by the gravitation force. Sorry, that is air resistance, push of air. Is it clear for you all? කවුරුත් නේ හරිද තේරෙනවද නැද්ද yeah, if there's a R resistance, so it's not called the free falling, right? So then the resultant acceleration will be different. It's not g then. When we consider about the acceleration, that resultant acceleration is g minus the acceleration produced by the R resistance. So resultant, we call the free falling when the case of the object is acted under weights only, right? If rather than the weights, if there are many other forces acting on it, we can't say it's free falling. If it is free falling, means that the forces acting on the body is only the gravitational force, that is weights only, right? So but when you write the potential energy, you can write as mgh. That is not depend on the g. That's that acceleration is not, you are not going to put there, because it is always mgh, because that is a gravitational potential energy. The acceleration of gravity we used to do the potential energy, because this is the work done by the gravitational force only, and this is the work done by the resistance force acting on it. And if you are writing here the total work done, that the resultant force acting on it, the resultant force acting on this is mg minus f, and multiply by the displacement is never. So that's why we get the minus value. Is it clear then? Alright, we go through the another question. It's important about this work energy theorem, right? Using other things, other means that energy conservation or other cases, you cannot calculate this. You need to use this work energy theorem. If not, you need to find this air resistance, forces, air resistive force, and then you need to do it. Because you can find it actually. Have the total energy you can calculate, and also you can find the force acting on it using F equal ma, because the resultant acceleration is not g there. So it is the a, you can put a or something like that, and then the acceleration of gravity you can reduce. So then you can find the actual acceleration, the effective acceleration when it's falling. Okay, I'll give you another question then, right? Right there. A, B, C, D is a smooth track. ABCD is a smooth track. Smooth track. An object of mass simple m is released at A. An object of mass simple m is released at A. Released at A as shown in the figure. As shown in the figure. Find the velocities at B, C and D. First part, right? Find the velocities at B, C and D. The second part, if the object is stopped at E, stopped at capital E, what is the coefficient of friction? What is the coefficient of friction between D and E? So what is the coefficient of friction of the surface between D and E? D and E. Okay, I will give this 2 meter. This is 1 meter. This 1.5 meter, and from D to E 10 meter. Asking velocities at these points, and when it stopped there, we given the question, if the object come to there, it will stop. And draw it and then carefully. The coefficient of friction and the velocities at these other points. right? Right, let's see then. You can use the energy conservation of mechanical energy, because there's no friction, it's smooth track from D to A to D, so you can use the energy conservation. That's potential energy at this A. I'm writing that total energy at A, that's equals total energy at B, right? This is mgh and ha, and this half m v is car, that's a b, and let's say the velocity here is v is car, and it's also because this level will be taken as the potential energy 0 level, so you can write that v is at height 1 meter, so then you can write and mghb, mass cancel, and this g is 10 n meter to meter bound, that's vb is car over 2, and this is 10 into 1 meter, so it's 10 into 20, and vb is 10 is square root of 20, that's 2 root 5. So velocity at b. And velocity at c, the same thing you need to do. A, the potential energy mgh, I'll take the substitute mg into 2 now. That's a kinetic energy at c, it's half mass into vc square, and the potential energy at c, that is mg into 1.5. so m cancel, here 20, this is 15, and 5 there, and multiply by 2, 10. So then the cc equals the square root of 10 meters per second, that is 3.16. and d, same thing apply for a and d also. The energy conservation can use, here the energy is mgh, the d, the potential energy is 0, so directly it's converted to the kinetic, half m vd square. vd equals square root of 40, that is 2 root 10 meters per second. That's the velocity at d. These are the velocities, so then we need to find the coefficient of friction within the EV. Just stop it there, so you can find the deceleration. Say v square equals u square plus 2s. Finally, this from d to e we apply. So v square 0, u square is the velocity at here, that is vd square. That's distance traveled in during this is divided de. So then substitute the value 0, and this is square of this is square of this is 40. Going to A into D distance is 10. Then A equals minus 2 then. So the force acting when the object is moving, force acting on it, opposite because the retardation force act on it, force is mass into the acceleration. So this is mass into 2. That is the frictional force acting on it. This is the friction. And the mu equals the friction divided by the R. Here R the normal reaction, right, it's equals to the weight of the body. This case. So this is 2A and this is m into g is 10. So m cancel, this mu equals 0.2. That's the coefficient of friction during this part, right? Is it okay? Okay, we'll discuss some theory and then come back to the questions again. Okay. Early resistance. Right. Then write the power. Power. This is the rate of work done, right? That's the work done divided by how much the time is taken to do this work, total work. So average average power we are writing. That's because in the systems when they are working, always the constant force is not applied on it. You know, when we consider about the vehicle, the force resultant force acting on the vehicle is changed during its motion, because it's accelerate, decelerate, and some cases moving at the uniform velocity. So then its velocity is always changing, so acceleration also can change, and the forces acting on the body also change, right? So then we can't say about the constant power it's working. The engine will work with the average power. So we are considering the average power is then, and if someone wants to know about the power at a particular instant, so it's called the instantaneous power. So instantaneous power and the average power means the total difference then, right? The average means throughout all the motion considered, right? All the work done, how much the total work done, you divide by the total time is taken. So instantaneous power means that's the work, the power or the rate of work done at a particular instant of time, you can say, right? So as example, let's say there's a, when a man is working, normally when he starts working, he can work very quickly, and then, but with the time he get tired, and then he can't work he can't work quickly as he done in the beginning, right? So that's the one. That means we ගෙවල් හදනකොට දැකලා in the houses උදේට සාමාන්‍යයෙන් ඔය බ්ලොග් ගල්ස් බඳින අය බ්ලොග් ගල් බඳින එක ගත්තත් එහෙමයි. උදේට දැන් පැයක් විතර යනකොට ගල්ස් 10 15 50ක් විතර මැදලා තිබ්බා කියලා. හැන්දෑවේ පැයක් විතර යනකොට මැදලා තියෙන ඊට වඩා අඩු රේට් එක. Because they tired, and then the power of the working will be reduced. So that's why we are considering average power then, right? Okay, that's first we write there. We'll discuss this. The right work done per unit time. Work done per unit time is called the power. Is called power. Work done per unit time is called power. Right? If an agent does work, delta W, if an agent does work delta W in a small time interval delta T, then average power delivered can be written as right, the average power is total work done with total time taken, so that is written as the P plus delta W over delta T. So this is average power, right? Let's write this equation. then right there the SI units of power is it's watt. SI unit of power is watt, that is 1 joules per second, that's equals to 1 watt. The other units, that's also you can use the horsepower, HP. Oh, yeah, yeah. Thank you, thank you. 1 horsepower, that is HP. That's equals to the 746 watts. That is horsepower. Normally in all engines or train engines, the power is rated as horsepower thing. That's 800 horsepower, 1000 like that. And also right there, the power is a scalar quantity. It's not a vector quantity. It's a scalar, right? Power is a scalar. Just like power, that's work done. Work done is also a scalar, the power is also a scalar. The different system is working, the power is different, right? In your home also, that's different electrical instruments, they are having a different power. They can 100 watts, 50 watts power. Normally, you know that's a small calculator we consider. Its power working is 50 microwatts. And torch bulb or torch lights we consider it will be some small torch lights. The power will be that's 4 watts, 4 milliwatts. Some torch bulbs, right? And the loudspeaker, when we consider loudspeaker, its power is about that's a big problem. It's the power, because the power is cut now. Could you give me a once mean? No, it's no power. Okay. What I mean on it? Can you see the board? So we'll finish this power part and then finish the class. That's small, I think take small time. I don't know that whether power is cut at 6 because schedule time එක නෙමෙයි මම දන්න විදියට. පොඩ් එක ක්ලියර්ද පේනවද? චුට්ටක් එක් කියන්න. නැත්තම් රයිටින් පෑඩ් එක බලමුවත් ලියන්න. Okay, then okay. ඔයාලට අකුරු ටික පේනවා නම් මම ලියන this enough actually. Okay, I will erase this. It's about power. So then write the instantaneous power. Instantaneous power means that is the power at an instant of time, right? So then write the instantaneous power. Right under that, the power at the instant of time is called instantaneous power. Power at an instant of time. Okay, sorry for that because I have instantaneous power, right? So it's a power at an instant of time, at any instant of time, right? And you can write this power, instantaneous power is in this way. Let's say this power equals the W over delta T. That's work done, we know that it is the force acting on the body multiplied by the displacement. Let's say the constant force acting on the body and the displacement will change. Delta Fs divided by delta T. If a constant force applied, so delta S over delta T. So delta S means the displacement here, right? Displacement, right? So displacement divided by the time taken, that's the rate of change of the displacement, is the velocity. This is the instantaneous velocity, that's the velocity of the body at the time you considered, right? So I'm writing this, that is instantaneous velocity. So then the power you can write as force multiplied by the velocity. So we can write the instantaneous power. If any instant of the velocity is v, so the force acting on the body is F. The power of the engine working, that is F. Right? Get an idea. You can write this is in the vector form also. The force is a vector and velocity is a vector. So in this format you can write if the force and the velocity has the angle between them is theta. So you can write this Fp cos theta. If you have there's a vehicle is moving with the velocity v here, let's say the force is applied on the body in theta degrees to with the velocity here. In this kind of case you can write in this way, Fp cos theta. If not, always we consider the force along this horizontal line, that's the direction of this velocity. So you can write this in, this is the power, also you can write the F into V, force into the velocity. For a vehicle engine, if you write the power of the engine, so there's a force applied on the vehicle means it's a traction. We call it a traction. Traction is a force given by the engine to the motion. The resultant force acting on the vehicle is then the traction. You need to subtract the air resistance and all the resistive forces like friction, air resistance, and every resistive forces you need to subtract. So the net force you can calculate, right? That to overcome this all the forces, the engine should given a force, that's traction will there. So if that traction is equals to this, that's we call the tractive force or traction. Like that, if the tractive force is equals to the normal, that's all the resistive forces like friction and air resistance. So then the vehicle is moving with the constant velocity. When it's moving the constant velocity, then you can write the power of its working. That's a force applied by the engine multiplied by the velocity of its movement. Right? So that's the way we write. I will erase this, then we will write there. Right, let's consider a vehicle of mass simple m. Consider a vehicle of mass simple m. This is moving with velocity v. This is moving velocity v. V is constant, right? Constantly they are moving. Like in this case, to move the vehicle the constant velocity, the engine should given the force which equals to the total resistive force. That's let's say about the friction or total resistive force. And here this F1 we call this is a tractive force. Tractive force or traction. That is traction, which means the force exerted by the engine, because the engine will rotate the wheels and then given a force, and this is resistive force. Resistive force, that is such as friction and air resistance. Total one we consider the resistive force. When it's moving with the constant velocity, right, as v constant, so you can write then the F1 equals F2. So the power of the engine, power delivered by the engine, you can write then that is the tractive force multiplied by the velocity. Velocity at that case, when while it is accelerating also, if you want to get the power, to find the power, you need to consider the power that at instant of its you consider that velocity, you need to substitute there. If you want to get the average one, then write the total work done, you calculate and then divide by the time. So then here the power equals, that's the tractive force is F1 multiplied by the velocity. If the tractive force is greater than the air resistance, all the resistive force, then only the vehicle can accelerate. If tractive force is less than this total air, what's happened? If let's say the friction is greater than tractive force, then the vehicle is not moving, no work done. Right? It will be at the same place, so no work done. But in the vehicles, we know that while it's moving, the resistive force, so air resistance applied on the vehicle while it's moving is proportional to the square of the velocity. If the velocity increases, the air resistance also increases. You know, in these days, the humans having a problem with the lack of petrol, no? So then what they do, they will moving with the smaller speeds. So how they can save the fuels when they are moving with the less speeds? So that's the case then. If the small the speeds, that's the air resistance also is small. So then your engine should not apply the larger force to run the vehicle. So then you can save some fuels. If not, if you are moving the higher speeds, so the rate of fuel combustion also much higher, because of you need larger power to run the vehicle there. So high the power means higher the fuel consumption, so its fuel will consume more there, right? So that's the way you write this is power. You can identify this when the vehicle is moving along an incline, so then you can consider the weights of that's if let's say if vehicle is moving like this, then what's happened? The engine should give the power to overcome the component of the weight also, other than the resistive force. So then the engine should apply larger tractive force, so then it's consume more fuels. That's why, you know, when the vehicle is climbing up for the mountains like this kind of motion, so it's very difficult to move, right? So the power of its working is much higher. But if a vehicle is moving down an incline, right, so then the weight, the component of the weight come towards it. If this is sufficient to overcome the friction, so then without the engine also you can move. Right? Because if this weight component of the weight is sufficient to overcome the all total resistance force, which you can switch off the engine and then the vehicle can move. We call it we are moving with the neutral. Engine එක neutral position එකේ තිබ්බා නිකම්ම තල්ලු වෙලා යන්නේ. So that's why මේ වගේ එකක neutral යන්න ගියොත් මොකද නික පල්ලෙහාට එන්නේ. හරි. So මෙතනදී engine එක off කරලා වුණත් යන්න පුළුවන්. If you use the engine, you can increase the velocity or increase the power up. Right. උත්තර ලියාගත්තානේ මේ වගේ දෙම් ගණන් හදන්න තියෙන්නේ මෙන්න මේ වගේ අපි බලමු ඊට කලින් අපි තව එක පොයින්ට් එකක් අද දවසට කියලා මම නවත්තන්න මේ power නැති හින්දා. Next point, right, efficiency. Power again අපි will do some questions. The right efficiency. I will come to some question with this power part and then first discuss the other part. Right efficiency. ඒක ලිව්ව නේද උන්? සත්‍යයක් වනේ මම කිව්වොත් එක්ක. It's important. That's the last part of this session. This is efficiency. That's eta we can use efficiency. We know this all the machines or engine or any system. If we consider about light also, so all the machines, what we do using a machine, some form of energy convert to the another form. if you consider the light bulb, so we convert electricity into lights, right? So heater, sometimes it's convert electricity into heats. In the mechanical systems also do this, right? In some cases, some potential energy they convert to kinetic, or rotational kinetic energy converts to the translational kinetic energy. Like that, they convert energy from one form to another. When this confirm this conversion of energy, what's happened? So when they convert energy, the total energy given to the system will not be output, right? Because some energy will lost to the surrounding as a heat and sound, so other form of energy also. So then there are some loss, the mechanical energy loss. So efficiency means how much the useful work you do, right? How much the useful work done by the machine with respect to the total energy given to the machine, right? So it's defined as a ratio of the output work done to the total input work done, right? So we can define it as a power, we can define it in terms of energy, and we can define it in terms of work done, right? Efficiency is then you can remember that. So it's normally expressed in as a percentage. They are writing it as a ratio, but multiplying by 100 we can express this as a percentage. Okay, first to write under the efficiency, right there, the efficiency of a machine. The efficiency of a machine is defined as the ratio a ratio of output work done to the total input work. The total input work. Right, it is generally expressed in terms of it is generally expressed as a percentage. It's generally expressed as a percentage. As a percentage, right? Efficiency of a machine. The efficiency of a machine can also be defined in terms of efficiency of a machine can also be defined as a percentage can also be defined in terms of energy or power. Okay, you can write that is efficiency. You can write this as an equation. It is a efficiency, that is eta is equals to the, right, then That's output. Actually we write the output useful energy, right? Useful energy work done, because unwanted energy work done we don't need to write it, because heat and sound is not the wanted one for a heater, but heat is a wanted. So then total input work done multiply by 100. Generally we express in terms of as a percentage, right? The heater you can write then that's work output, this work input work to 100%. Yeah, and if not you can write and also you can define this as that eta. We can write the energy output output energy, the total energy given to the system, that's the input energy, multiply by 100. In symbol we can write as E out divided by E in multiplied by 100. Another way we can write it's eta equals to the power output power divided by the input power input divided by 100. Input power means that how much the rate of the power, that's a power given. That's, let's say for a vehicle the power is given by the fuel burning, and then it's convert energy to the mechanical energy work, mechanical work done. So eta you can write as power out, the power in multiplied by 100. So if they considering the power, that's the power, you can write the efficiency this way. If they are considering the energy, you can consider the power in this way, or use the work done also. If the efficiency of a machine is 100%, we call it the perfect machine or ideal machine. But in a universe there are no any ideal machines yet, right? Because we know that on all the cases it's some amount of energy we lost during any work done. Okay, finish the writing, let me know. Okay, then write there after this, write if the efficiency of a machine is 100%, if the efficiency of a machine is 100%, it's called an ideal machine. It's called an ideal or perfect machine. Ideal or perfect machine. The perfect machine can do work. The perfect machine or ideal machine can do work without energy loss. Can do work without energy loss. There is no ideal machines on earth. So there is no any ideal machine on earth. All the machines lost the energy, all the machines lost the given energy, all the machine lost some part of the given energy, correct? All the machine lost some part of the given energy as heat, sound, extractor, right? So heat, sounds, and any other forms also there, because that's loss means that is not the useful energy to that system. So in different systems they are having a different usefulness, right? So that's why. So that's the way we consider this power and efficiency. Okay, small example එකක් අපි බලමු. මේ කියන්නේ example නෑ නෙමෙයි ගන්න. ඔය වැඩිපුර මොකලන්ට එන questions එකක් නිකන් ඔය electric motors වගේ අපි mechanical work done එකක් කරගන්න use කරන mechanical motor systems වල කොහොමද නිකන් power එක හොයන්නේ කියලා. එකත් ඔක ලියා ගන්න මෙහෙම example එකක් දෙන්න නෙමෙයි. Power of pump to lift the water from the well. Right, this as a topic. Power of pump to lift the water from the well. Lift the water from the well. From the well. Right there, let us consider a pump. Let us consider a pump lifting water from a depth, simple H. Lifting water from a depth H. So it's simple H, right? Simple H. Depth, simple H, of a well, right? Of a well, and delivering at a rate of that's delta M over delta T. Delivering at the rate of delta M over delta T. Okay, at a rate of delta M over delta T with a velocity V, right? With a velocity V. Okay, here I'm considering like this. It's a දැකලා දෙකේ වතුර අදින්නේ බට දාලානේ. So it's a well. නිද තියනවා කියන්නේ උඩට water level එකේ මෙතන නම් උඩට ගන්න, right? කියන්නේ අපිට මේ පම්ප් එක මේ ඕන තැනක තියලා මෙතනින් උඩට තල්ලු කරන්න පුළුවන් කොට. අපි උඩ තියලා වෝටර් එක තියලා පම්ප් එක මෙහෙම කන්සිඩර් කරන්න පුළුවන්. You can consider it like this. So මෙතනින් පම්ප් එකෙන් දැදලා then this velocity v එකෙන් හෙලෙන. Anyway, you can consider it, but the height h you think that's height hv lift the water and then ejected with the velocity v. This is the pump, right? The amount of water come at the rate delta m over delta t. The delta m amount of water will come, that's come out at the time delta t. That's the way you considering, right? You can write that things there. Let you can draw, and then you can draw this and then write. Suppose I'll write there. Suppose delta m amount of water delta m amount of water is delivered in time delta t. Right, suppose delta m amount of water is delivered in time delta t. Okay, it's delivered, that's delta m amount of water is ejected out at the time delta t, right? With the velocity v, I think like this. So then the total work done in this system, that's work done. What is the work done then? Is they lift the water. Let's say the work done at the time delta t. So they lift the water amount delta m. That's the potential energy increase delta m g h then, right? Delta m will come to the top, and then delta m g h is the potential energy change. And they ejected out the water, that delta m amount of water with the velocity v. So then the potential energy, kinetic energy is half delta m v square. That is the total work done during this time, right? So then I'll write that's work done in time delta t, that is potential energy change PE change plus the kinetic energy change, right? Change. So we can write that is, let's say this is W and this is delta m, right? Delta W, this delta m GH plus half delta m v square. Okay, so then the power delivered you can write power delivered, that's capital P is the delta W over delta T. So you can divide this by T then, write the equation, that's delta M over delta T, that's the rate of mass ejected, that is GH plus delta M, that's a half delta M over delta T v square. In the case of the water ejecting out, because we cannot get a particular amount of water mass, so the rate of water ejected out, even if you know, so then you can calculate this. So actually we know that is delta M over, if you remember that delta M over delta T that is the mass of water ejected out is the density of water. This rho is the density of water, let's say. So the density multiplied by the rate of volume ejected out, rate of flow we call. Okay, so if the cross section is A, this is, you can write under the momentum conservation, we write this when the liquid jet apply the force on the wall. Remember this rho equals that delta V over delta D is AV. That's the cross sectional area of the tube multiplied by the velocity, right? So you can substitute this there and then write this. Therefore, then the power delivered is equals to the, that's delta M over delta D. You can take out from this equation, and it is GH plus V square over 2. So rho AV you can substitute for this thing, rho AV GH plus V square over 2. So this is the way you writing the case of a water pump, right? These are not the equation you need to remember, right? You need to know how to derive this kind of expression and then you calculate the values when they given. This is the way. If they need to lift the water only without any ejecting like so this velocity part becomes 0, then the other part will come. And efficiency, if the power pump is related, that's rated like its power is value 1000 watts or 750 watts, so that is the power input, right? The electricity you need to give that value you need to obtain, and this is the output power. It will not be equal then, so then the efficiency will be less than the other. So we will discuss some question in next week then. So you copy it down up to this point, and if you finish the writing, let me know, then we will stop the class because of it's getting much darker, so my light power is also reducing. If you finish the writing, let me know. Okay, then if both finished, then we stop the class from this point. You can go through this theory part and then come next week. We will discuss some more questions related to power, energy conservation and all the things connected. So then this part is actually finished. Then we will discuss the collisions between the two collisions. That's how the elastic collisions and inelastic collisions are. And then we will start the angular motion. Okay, if you finish, then you can go. Okay, God bless all, and thank you for the participation. Goodbye and good night.